Good afternoon and welcome to today's IAC webinar, Physics for the Clinical Cardiovascular Sonographer. My name is Kelly Baer and I am the Creative Design Manager with Marketing Communications at IAC. Before we begin, I'd like to take a moment to review a few technical matters and let you know how you can participate in today's session. We would like today's webinar to be interactive, so we encourage you to submit questions. To do so, use the Questions tab located on the left side of your screen. Please submit your questions anytime during the webinar, as we will monitor questions throughout the presentation and try to answer as many of them as possible during the Q&A period. Also on the left sidebar, please note the Resources tab. Click on this tab for a link to today's handout, a PDF copy of these PowerPoint slides. Select the file name to download the handout. Lastly, in the lower left of the player, please note the Request Support button. If you experience any technical problems during this webinar, click this button. A technical expert will be there to assist you with any issues you may have. For those who like to take notes during the presentation, look to the right of the slides and click the Notes tab. There you will see a white text box where you can take notes on today's webinar. These notes will be emailed to you automatically at the end of the session. To be eligible for the SVU CME credit, you must be registered, logged into this webinar, then complete the survey. The survey will appear on your screen automatically at the conclusion of the live session and also be available from the IAC webinar portal for 3 business days. If you are viewing this webinar in a group, please be sure you are also individually registered and logged into this webinar on another computer or device so that we have record of your attendance today. Today's presentation is being recorded and will be posted at a later time for on-demand viewing. This webinar is a joint presentation of IAC and SVU. And now I would like to introduce today's guest presenter, Frank Miele. Frank Miele is the president of Pegasus Lectures, located in Dallas, Texas, which specializes in credentialing exam preparation and continuing medical education for ultrasound professionals. His background in physics, mathematics, and engineering led him to the design and research of ultrasound equipment. Frank has authored multiple books, educational videos, and exam simulation programs, and has lectured across the country to sonographers, physicians, engineers, and students. He has served on the faculty of the Society for Vascular Ultrasound and Society for Vascular Surgery and is credited with several ultrasound and medical device patents. And we are happy to have him with us today. And with that said, I will now turn this webinar over to today's speaker, Frank Miele. Frank?
Thank you, Kelly. Hello, everyone. And let's get going. So first, a quick review of the objectives. So I want to understand how angle correction is employed in spectral Doppler. Appreciate the nonlinear behavior of the cosine. Hopefully that doesn't scare you off. Learn why angular error still exists with angle correction. And learn that spectral broadening is exacerbated by larger Doppler angles. So those are the objectives for today. So I want to start off by reviewing the cosine. And we'll see why that's so important in a few minutes, but it's critical that we have a good understanding of the cosine so we can really understand angular effects in Doppler. So we'll start off by doing basically using an analogy. So let's say that we had a stick that's exactly 1 meter long. So I'm going to draw a stick here and say this is 1 meter long. And let's say it's parallel to the ground. And when it's parallel to the ground, we're going to call that an angle theta equal to 0 degrees. And now let's assume that we have, let's say it's raining, okay? And it's raining straight down. And so what you see is rain goes everywhere. But the stick blocks the rain, and we get a dry spot on the ground, a shadow, if you will. We could also talk about this being laser lights being pointed down. We can talk about the length of the shadow. This is not a trick question. What's the length of the shadow? Well, clearly, it's exactly 1 meter long, the length of the stick. So in other words, we're able to measure or tell the length of the stick by measuring it indirectly, by measuring its projection or its shadow. Well, what if we rotate it and don't have it parallel to the ground? What if it's at a different angle that's non-zero? So let's do that. So let's rotate it and say that's an angle of, say, maybe about 30 degrees. And what we can see is that the length of the shadow gets shorter. Clearly, the stick's length didn't change, but the length of the shadow did. And as the angle gets bigger, the length of the shadow gets shorter until we reach 90 degrees, in which case the shadow disappears. And so we have this issue in that we'd like to be able to measure the length of the stick, but there's an angular dependence. And wouldn't it be nice if there was some mathematical approach that says, hey, measure the length of the shadow and tell me what the angle is, and I can back out the angular effect and tell you the true length of the stick. And that's what the cosine does for you. So the cosine is actually a way of measuring the percentage of the shadow that you see that gets affected by the angle. So we're going to learn how to do cosines. So let's go to the circle. Now, where did the circle come from? Well, imagine I start with the stick laying on the ground. So here's the stick at 0 degrees. And I'm going to leave it anchored. And I'm going to remember, the stick is 1 unit long. Okay? And I could put other markings on the stick as well, kind of like a ruler, 0.5, 0.75, 0.25, and 0. And what I'm going to do now is I'm going to rotate it through angular space. So leaving this point anchored to the stick and rotate it. As I rotate it up to 90 degrees, we created this quadrant of the circle. I continue to rotate until I get to 180 degrees. Now I created this half of the circle. Well, if this point is 1 and this point is 0, you can imagine we're going to call this point -1. So here's -0.5, -0.25, -0.75. I'll keep rotating the stick through until I get to 270 degrees. And I'll keep rotating until I get back to 360 degrees. And lo and behold, I've created a circle. So we're going to use this circle as our means of learning how to determine cosines. So let's go to a stick that's better, a circle that's already portioned. And now what we're going to learn is what's called the basic angles. And the basic angles are the angles in the first quadrant of the circle. So the first 90 degrees, this is quadrant 1, here's quadrant 2, quadrant 3, and quadrant 4. And now the basic angles are the angles that are easily visualized in that first quadrant. And I have them labeled here. So clearly 0 degrees is easy to visualize, and 90. Well, 45 is also very easy because it's exactly halfway between 0 and 90 degrees. And what else is easy to visualize? Well, 30 and 60, because it breaks the circle down into a third, a third, a third. So we have our basic angles of 0, 30, 45, 60, and 90 degrees. Now what we're going to do is we're going to repeat our little thought experiment and come up with the cosines. So I'm going to build up a little table here of the angle theta and the cosine of the angle theta. Like I said, there's a purpose for this. What we're going to learn is that Doppler is very angle dependent and depends on the cosine. So understanding the cosines is critical to truly understanding Doppler. So at 0 degrees, we lay the stick down on the ground. We shine the light down towards the ground and read the length of the shadow off the ground, and we see the cosine is 1, or 100%. So at 0 degrees, the cosine is 1, or 100%. Okay, let's now put in 30 degrees. So we rotate the stick to 30 degrees, shine the light down, and we see the length of the shadow is here. And we can see clearly it's bigger than 0.75 and it's less than 1. Now, if we measured it accurately, what we'd see is it comes out to be about 0.867, 0.866. Okay? But you can see that it's bigger than 0.75, less than 1. That value should make some sense to you. Okay? Now, we're going to rotate up to 45 degrees and drop it down. What you see is the cosine's just a little bit less than 0.75. The actual answer is 0.707. And now we're going to rotate to 60 degrees. And anyone who's done any vascular, as soon as they say 60 degrees, should start to shake uncontrollably. And here we have the cosine of 60 degrees is 0.5, or 1/2. So at 60 degrees, we only see 50% of the shadow that we'd see at 0 degrees. And then clearly at 90 degrees, the cosine is 0. So what we see is, in the quadrant 1, as we go from 0 degrees to 90 degrees, the cosine goes from 1 to 0. And then when we get into quadrant 2, So let's say I go over from 60 to 90 is 30 degrees. So let's go over 30 degrees from there, which makes it 120 degrees. What I see is the cosine of 120 is minus 0.5. And we see that 120 and 60 are the same basic angles. So whether you're doing a Doppler at 120 or 60, it gives you the same Doppler effect, same shift, except the plus sign tells you that it's going in the positive direction, and the minus says that it's going in the opposite direction. Well, similarly, we have 135 degrees, which is the same as 45 degrees, minus 0.707. And 150 degrees, it's the same as 30 degrees, minus 0.866. And 180 degrees is equivalent to 0 degrees, gives you the value of minus 1. At 270, the cosine is 0. Oops, going a little crooked there. And at 360, we're back to 1. Okay? So this is basically the values of the cosine. What we're going to do now is we're going to graph that. And I'll have that on the next slide. Oops. We have those values there. Let's just erase the ink on the slide so you can see those cleanly. Okay, there's the values. What we're going to do now is we're going to graph that on a graph. So here what we see is the angle theta being plotted on the axis, on the horizontal axis, and on the vertical axis we have the actual cosine. So we can see that here is 45 degrees, here's 60, here's 30. Here's 0 degrees. At 0 degrees, the cosine was 1. 90 degrees was 0. 180 was minus 1. And we can see that the cosine is a very non-linear shape, which means that as I go from 0 to 10 degrees, the change in cosine is different than when I go from 10 to 20 degrees. That change is bigger. And I go from 10 to 20, that change gets bigger. And it gets bigger and bigger and bigger as the angle gets closer and closer to 90. And then what happens as I get closer to 180 degrees, the change with angle becomes less and less. So the rate of change of the cosine is smallest around 0 degrees and around 180 degrees, and greatest when you get around 90 degrees. Okay? So hopefully this makes it clear to you that the cosine has a very, very nonlinear behavior, meaning 10-degree error around 0 is not the same as a 10-degree error around 60 degrees, which is not the same as a 10-degree error around 180 degrees. Okay? It varies as the angle gets bigger and bigger. Okay? All right. So now we're going to learn about the Doppler effect, and then we're going to put the pieces together. So let's start by actually deriving the beginning of the equation. Now, when you've learned about sound, you've learned that sound is a longitudinal wave, and you've probably seen that picture drawn like this, where you see these lines, and we talk about these lines representing maximal compression, and then we talk about rarefaction, the space in between the lines. We say sound propagates through a series of compressions, rarefactions, compressions, rarefactions, where the particles move back and forth along, hence the term longitudinal, along the direction of the wave propagation. Okay, so this is a longitudinal wave. Okay, and that's what sound is, a longitudinal wave. So let's start with a train. It's going to blow its whistle. But now we're going to look at the sound emanating in all different directions from this train. So the train's not moving. It's going to start with a velocity equals 0. And we're going to look at the sound propagating out in all directions. So these are supposed to be nice concentric circles. You'll forgive me the fact that they're not going to be perfect. Oops. Okay. And what we see is, let's just redraw this last one because it's a little bit too far off. Okay, there we go. So now let's put an observer on this side. We'll call it observer A. And on the other side, observer B. And we're going to put in the ground. Now, both observer A and observer B hear the same pitch whistle. What you can see is these dark lines represent compression, and the spaces represent rarefaction. So what you see is the sound is emanating in all different directions, radiating out, okay, in circles, okay? And both observer A and observer B hear the same pitch whistle. But now, let's see what happens when we put the train in motion with a velocity, so it's not 0 any longer, okay? We're going to leave our same two observers in there. So here's our train. And now it has a velocity that's not equal to 0, so it's moving. Now, at the first moment when the train blew its whistle before, when it gets to the exact same location as it was before, it's going to blow its whistle. After some amount of time, that first wavefront is going to reach out the same distance as it had before. Okay? Now, some amount of time later, the period, the next compression will come out of the horn. But what's the train been doing during that time? It's been moving. So let's say the train's moved this distance based on its velocity. So it's been moved up this far. Well, the next wavefront will still have moved the same distance from the train, but since the train has moved closer to A, wavefront will be physically closer to A than it was when the train was stationary. What we see is where the original wavefront would have been here, it's moved up by the distance of the train. Conversely, relative to observer B, the original wavefront would have been here, but it's moved up again because of the train's motion, and it's here. So we get this circle that looks like this. And we can see that these compressions, the distance between compressions, and that's referred to as the wavelength, the distance between compressions has gotten smaller. And conversely, relative to B, the distance between compressions, the wavelength, has gotten bigger. Some amount of time later, the train's moved further. Whoops. So let's say the train's moved up this far now. So the next wavefront will be up here. This one will be here. And what we see clearly is observer A sees a wave with a shorter wavelength, which sounds like a higher frequency. And observer B sees a lower wavelength, which sounds like a lower frequency. A longer wavelength, oops, let's rewrite that. Longer wavelength, so they see a lower frequency. And you've all heard this effect. If you've heard a train going by you at high velocity or a race car, and you hear that change in pitch, you hear, it goes from high frequency to low frequency. So notice, observer A is seeing an increased frequency, so we're going to call that a positive shift. And observer B sees a decrease in frequency, so we're going to call that a negative shift. So we now should understand what the Doppler effect is. It's an apparent change in frequency caused by a change in wavelength caused by motion relative to the observer. And what is so important about that term, relative to the observer? Well, this is going to refer to our angular aspect because notice, observer A saw the exact opposite effect as observer B, saw a negative. And because the train was moving towards observer A, we saw a positive. Because the train was moving away from observer B, we saw a negative. In fact, we could say if the train is moving towards observer A, that was at 0 degrees, and he saw a positive 100% of the shift, and observer B was away from him, it was at 180 degrees, and so we'll say it was minus 100% of the shift. Okay? And hopefully that should look familiar to you because it should look like the beginnings of what we just learned about the cosine. Okay? So we don't have time to derive the entire Doppler equation today, but we can basically come up with an idea of what the equation is, and we'll write out the equation. So what we just saw was that the Doppler effect is caused by a change in wavelength. And so my first question to you is, do you think that the Doppler shift would get bigger or smaller as the velocity increases? So we started off with velocity equals 0 and there was no shift. And when we had some velocity that was non-zero, we saw a shift. So clearly, as the velocity gets bigger and bigger, the Doppler shift is going to go up. So we'd say that's proportionality. So we're going to say the Doppler shift is proportional to the velocity. And that's the beginnings of our Doppler equation. Well, we also just said that the Doppler effect is caused by a change in wavelength. So I have a basic theory here that says basically anything that affects the Doppler shift, the wavelength is also going to affect the Doppler shift. And we know the equation for the wavelength is lambda equals c over f. So we know that both c and f are going to have to be in the Doppler equation. And we know one more thing. Because they both impact the wavelength in opposite directions, wavelength is proportional to c and inversely proportional to f, they're going to be on different parts of the equation. So We're going to write out the Doppler equation now and say the Doppler shift equals 2 times the operating frequency times the velocity divided by the propagation speed. And now the only thing we have left is the angular effect. And what we just saw a moment ago was that when the angle was 0, we saw a positive shift. And when it was 180 degrees, we saw a negative shift. So if we multiply by the cosine, and the cosine is 0, we get a +1, positive shift. When the angle is 180 degrees, we see a negative value, negative shift. And we now have the Doppler equation. Now, let me just point out one other thing to you. In the experiment that I did where I had the train moving with observer A and observer B at 0 degrees and 180 degrees, we saw a +1, 100% shift, and -1. What if we put observer C up here at 90 degrees? Now, at the moment that the train hits this location moving, remember the effect is caused by a change of wavelength towards or away from the observer. Well, is the train getting closer to C? No. Is it getting farther away from C? No. Therefore, there's no effect. Cosine 90 is 0 degrees. What if I put another observer here, D, at say 60 degrees? Is the train getting closer to D? Yes. But is it getting closer to D at the same rate as it is to A? No. Because it's moving in this direction, which is closer to D, but not straight at D. And we know what amount to C. Cosine 60 is 0.5 or 50%. So now this equation hopefully makes sense to you. Okay, so here we have the Doppler equation. We have the fact that the Doppler shift equals 2 times the operating frequency, the transmit frequency, times the velocity, what's moving, divided by C, times the cosine of the angle. All right. So now what's this idea of angle correction? Well, as we just saw, the amount of Doppler shift you detect depends on the angle at which you're actually insonifying the blood. So if the blood is moving at an angle that's other than 0 straight towards, or 180 degrees straight away, we're not going to get the full Doppler shift. We're only going to get a percentage of it based on the angle. So this cosine theta is there to adjust so that the Doppler shift that we measure when it's not 100%, we can correct it so that we get the true velocity out of the equation. Well, this implies that if we use angle correction, we should be able to correct for the angular effect, and therefore it shouldn't matter what angle we use. So theoretically, what angle we use should not matter, and that's true theoretically. Theoretically, because we're going to apply this cosine theta and correct for the angle, it shouldn't matter. So that begs the question then, why are we discussing this? If that's going to fix it, why are we discussing this? Well, let's take a look and see how we actually employ the equation, and then we're going to look at real world, okay? So we're not really interested in the Doppler shift. What we're really interested in is the velocity of the blood. So we're going to use basic algebra. When we want to solve for V, so what we do is we basically multiply both sides of the equation by C, which becomes the second line of the equation, and we want V by itself. So we divide by everything else that's next to it. So we divide by 2 on both sides. What if we do one side, you have to do the other. We divide by the operating frequency on both sides. And we divide by the cosine on both sides. And we end up with, clean that up now, this equation that you see right here, that the velocity can be determined this way. Now look, we know C, because it's assumed in the body, right? We know that speed of sound in the body is 1540 and blood 1560, so we know that. We know the operating frequency, because as a user, when you put in your transducer and you push the button, you say, I want to do my Doppler at 2 megahertz, at 3 or 4, you've chosen it. So we know the operating frequency. So this is known. 2 is a constant, so we know that. The Doppler shift is what the system measures. So we know this as well from the measurement. So that only leaves the cosine of the angle theta. And if we know that, we can tell you what the velocity of the blood is. And this is what I want you to remember as we go through the lecture, that basically when we apply an angle correction for the velocity, we do so by dividing the Doppler shift we measure by the cosine of the angle. So the velocity that we tell you on the ultrasound system is proportional to 1 over the cosine of the angle, okay? So in other words, we measure this. If we know the angle theta, we take the cosine of it, and we divide our Doppler shift by it and multiply by these other terms, and I can tell you what the true velocity of the blood is, at least theoretically, okay? So the question now becomes, why 60 degrees? And we haven't quite answered yet why we're still talking about this, but we will, because, as I said, it's theoretical that this should work perfectly, and it doesn't. So why 60 degrees? Well, the early days, there was only mechanical transducers, and according to Gene Zieler, who worked in Strandis's lab, the calculations had to be done by hand, and he was the one who had to do the calculations. This was before there was a lot of processing. And so since he had to do the calculations, and the cosine of 60 degrees is 0.5, and if you divide something by 0.5, that's the same as multiplying something by 2. Well, that's pretty easy math. So he said 60 degrees seemed like it would be a pretty good place to start. Okay, so 60 degrees seemed a pretty reasonable place to start. So then the early days of ultrasound and vascular started using pencil probes. Well, with pencil probes, without angulation, here's the problem. So here's a neck, here's a carotid. If you put a pencil probe on there looking into the neck, that gives you a 90-degree angle, which gives you no Doppler shift. So that clearly doesn't work. Well, turns out we can angle the probe about 30 degrees into the neck before we start to impinge actually on the carotid. Well, if you angle about 30 degrees, that creates about a 60-degree angle. And there comes our 60-degree angle again, right? And again, as we said, the math is easy. So a whole bunch of work was done, correlation studies were performed, and hence the birth of the standard 60 degrees. That's where 60 degrees came out of. Then came electronically steered transducers, where we had these large linear arrays, and we could steer electronically at different angles. And the question came up, what angle should we use? And the answer said, well, since we've done all the correlative studies at 60 degrees, we probably should stay there. Okay, so now here's a question for you. Because I haven't said why it matters what angle we're at yet, but look at this picture and guess what the error is. And we're going to come back to this. I'm not going to give you the answer right away, but what is the error and how much is it? So do you think that this is done correctly, this Doppler? And the peak velocity is measured accurately, so there's 0% error? Or do you think we've overestimated by 12%, overestimated by 20%, underestimated by 20%, or underestimated by 35%? Let's give you a second to look at that. Okay. Well, here's the real world. Notice that when we do Doppler, we set what's called a flow indicator. So we have here's our Doppler gate. This is our Doppler steering line. And the flow indicator has been set this way, such that this is the Doppler angle. And this would say an angle of 60 degrees. And so this is how we tell the ultrasound system what the Doppler angle is, by setting the flow indicator. When we tell the system the angle, we can then put that in the equation and correct the velocity. Well, does anyone truly believe that the blood is actually moving in this direction in that vessel? But quite frequently people say, well, I want to set it at 60 degrees. It says 60 degrees. But the whole point is that the flow indicator is supposed to be aligned with the actual flow, which is this way. And as you can see in this case, that would form an angle of 90 degrees, which would give me virtually no Doppler shift. Okay? So we have to be careful that the flow indicator must be aligned with the actual flow. And that will give you a hint as to why there was an error in the previous picture. Okay? So if we look at this, and we now see, I'm now going to ask a slightly different question. Let's change ink colors here so it'll show up better. If I extend this flow indicator, you can see that it is not aligned to flow, and that the angle specified is incorrect. So whereas it says that the Doppler angle is 40 degrees, that's what it tells me. tells me right here the Doppler angle is 40 degrees. I will tell you that if I went back and remeasured it carefully, the actual angle is 55 degrees. And it says that the measured peak systolic velocity is 67.5 centimeters per second. And so my question to you is, what is the true peak systolic velocity? So is it 67.5? Is it 50, 100, or 135? Well, hopefully no one picked 67.5 because we know that we specified the angle incorrectly. So if we angle corrected incorrectly, the velocity that's being displayed is incorrect. So the answer cannot be 67.5. So that leads you down to these choices here. So let's see how we do this. So I'm going to show you two different ways of doing this. One is the mathematical way, and one is basically just using the theory what we said, okay? So I told the system that the angle was at 40 degrees, okay? Where the true angle should have been 55. Well, the cosine of 40 degrees is bigger than the cosine of 55 degrees. And remember what I told you had to remember? The velocity that we tell you is related to inversely with the cosine of the angle. So if I told you the cosine of 40 degrees, which was a bigger number, I divided by a bigger number than I should have, which means the velocity I told you is smaller than it should be. So that means the answer has to be bigger than 67.5. It can't be 50. So now the question is it 100 or 135? Well, if you remember that graph of the cosine, as I go from 40 degrees to 55 degrees, it's not likely I'm going to get a full factor of 2 change, right? I mean, it just seems like a huge change. So going from 67.5 to 135 doesn't seem likely, so the answer is going to be 100, okay? And that's how I can do it without math. Now I'm going to show you how I can actually do it with all math and get the actual answer. So the actual answer comes out to be about 100. And what you see here is that, remember, the velocity I had given, I had divided by the cosine of 40 degrees to come up with 67.5, but that was wrong. So to correct it, what I'm going to do is multiply by the cosine of 40 degrees to undo the bad correction. Does that make sense? So realize, when the system calculated the velocity, you told it the angle 40 degrees, so it divided by the cosine of 40 degrees. So to undo that correction, I have to multiply by the cosine of 40 degrees to make that correction go away. Now I have to correct it by the right angle, which means I have to divide by the cosine of 55. When I do that, you come up with an answer of 90.2, which is closest to 100. And now what I'm going to show you is that I redid this study correctly now. And what you'll see is that this flow indicator is now correctly aligned with the flow. Can you see that? And it says that this angle is 6 degrees. And I did that by changing my steering, okay? So by changing the Doppler steering, I changed the angle, it's now 6 degrees. And I remeasure the peak velocity, and lo and behold, it came out to 92.1, which is very close to what my calculator came up with, okay? Okay, so now remember that first question, what was the error? Well, I came up with an answer. The system said 67.5. We just said the correct answer is 90.2. So the error of that is 67.5 minus 90.2 divided by 67.5, which is a minus 33.6% error. And if the math is overwhelming to you, that's okay. Don't worry about it. But what I do want to point out to you, what's most important, is that you understand that first, the flow indicator must be aligned to flow. Then if it's not, the velocities you measure on the system are completely wrong. And as the angle varies away from that, the errors can get quite big. In fact, as we see here, almost a 35% error in the velocity, okay? So let's go back to our question. As we just saw, in essence, if we angle correct, but we tell the wrong angle, we're going to get the wrong velocity, okay? So now, why is it so important as to which angle we actually choose? Okay, remember, we came up with a standard of 60 degrees, but I'm saying that it actually does matter. That theoretically, it doesn't matter if I use 60 or 70 or 50 degrees because of this mathematical correction. But I'm going to tell you that it really does matter, and it matters quite a bit. So let's see why. So the real world. Here's my transducer. Here's blood flow. And so I align my flow indicator and say, I think this is the direction the blood is going. Now, do you really believe that even if you're extremely careful, that you can always get your flow indicator aligned with the actual flow within, say, plus or minus 1 degree? And the answer is no. Plus or minus a couple degrees? Maybe. I'll say plus or minus 5 is probably more reasonable in that plane that you see. But remember, when you look at a Doppler, right, and you put your sample volume down, you're only seeing a two-dimensional slice of a three-dimensional flow. So that's what this indicates here. We're only seeing one of these planes. We're not seeing the other plane. And it's possible that you're off an angle that way as well. So I'm going to say that I believe it's possible to be off by as much as plus or minus 10 degrees, okay? Now, it's more likely you're off by less than 5, but it's possible sometimes to be off by as much as 10 degrees, okay? And we can see why. We can't align the flow indicator exactly with the flow, partly because there's that other plane going in and out of the page, right, the elevation that we can't see, whether or not we're aligned with. Now, again, remember this picture I showed you, the cosine. And what we saw was if I was trying to do my Doppler at 0 degrees, let's say I'm off by 10 degrees. Well, the cosine at 10 degrees has changed very little. So doing my Doppler at 0 degrees and being off by 10 gives me a small error. What if I try and do my Doppler at 6 degrees? Being off by 10 degrees, cosine is changing very fast and gives me a much bigger error. Let's look at it another way. So let's say I'm going to do my Doppler at 30 degrees, but let's say it could be off by plus or minus 10. So that means it could either be at 20 or 40 degrees, as we see by these other green lines. So that green bar represents my angular error associated with by being off by 10 degrees, okay? Now let's say I do my Doppler at instead 50 degrees. Well, I can be off by 10 and plus or minus 10 again. That yellow bar represents the error, and look how much bigger that is. Now let's say I want to do my Doppler at 60 degrees. That red bar represents the error, and you can see how much bigger it's becoming. So clearly, as we get away from 0 degrees and 180 degrees, and we get closer to 90 degrees, our error gets significantly bigger. And this is one of the reasons why we try and stay at 60 or below and not getting above 60, because as we get closer and closer to 90, the errors blow up very, very rapidly. And in fact, this table shows that. So what we see here is basically the Doppler angle that we assume we're at. So this means we're at 0 degrees, the blood's coming straight at us. This says we're at an angle of 10 degrees, 20, 30, etc. This says we're off by plus or minus 10, so it gives me the cosine values. And this tells me how much my velocity is over or underestimated by being off by those 10 degrees. So let's just look at that for a moment, and we'll ignore this pressure side of the table for a second. And what we can see is that 60 degrees, being off by plus or minus 10 degrees, gives us an error of about 30%, plus or minus 30. By the time we hit 7 degrees, we're off by almost 50%. So we can see that as our Doppler angle gets bigger, any error we have with alignment to flow just basically causes huge errors in the velocity measurement. Now recall that using the modified Bernoulli's equation, we say that the pressure gradient is approximately equal to 4 times the velocity squared. So if we take our error in our velocity and we square it, that gives us our error in our pressure measurement. And we can see how dramatically the error in pressure measurements goes as we go as bigger and bigger angles. So clearly we want to avoid these large angles, okay? And it doesn't say that 60 is perfect by any stretch of the imagination, okay? But we want to make sure that we stay at 60 or below because the errors just really blow up exponentially as we go further, okay? All right, so this just shows a graph of that. And again, you can see percent error in velocity versus presumed angle. So we can see down at these lower angles, life is better. But remember, we can't really get to angles of 0 degrees or 180 degrees when we're looking at a carotid as an example, because the vessel runs parallel to the skin line. So it's really not possible to get to angles of 0 degrees or 180. We have to be at these larger angles. Okay, this shows the percent error, again, for the pressure gradient. Again, now look at how big these numbers are. Here's 100% error. And we can see how huge the errors become as we get up above these angles of 60 degrees, okay? All right, now there's another effect that impacts a reason why we don't want to be above 60 degrees. And this is what's called intrinsic spectral broadening, okay? And so what happens is this is actually, there's intrinsic and there's artifactual spectral broadening. And artifactual spectral broadening means that the spectrum we have spreads around the actual spectrum, making the peak velocity higher than it should be, and it starts filling in the spectral window below. Okay, so it spreads the signal, just as the name suggests. So here's why that happens. So this is supposed to represent a large transducer, like our large linear array. Here's a vessel like a carotid that's relatively shallow. And when we transmit, we don't transmit from one single element. We transmit from a group of elements. So the Doppler angle is measured from the center to the direction we set the flow indicator, and we say that's our Doppler angle. But what you should be able to see is that this left element actually has a bigger angle than the specified Doppler angle. And this right element has an angle that's smaller, which means if we use just the angle in the center, let me change the color so it shows up a little bit better for you here. Let's try green. Okay. Oops, didn't change. Try it one more time. Okay, so we can see this angle is less than the central angle. This angle is bigger than the central angle. So we divide by the cosine of the center angle. On some of them we overcorrect, and on some we undercorrect, causing the spectrum to fill in and to read a higher peak, causing this to happen. Well, why does the angle matter here? Well, let's see why. First of all, this problem gets worse as your sample volume gets shallower. And this picture shows why. So we see the spread from the left and right element looks bigger when we get closer and smaller as we get farther away. This is the same idea of why a star looks so small, even though it's enormous. We're so far away, we're way back here, that a huge star looks tiny from where we are. But as we get closer and closer to the star, we see that it gets bigger and bigger and takes up the entire sky. Well, it's the same thing with the vessel, okay? And with the transducer elements. So the transducer elements, the spread of elements, looks bigger as we get closer. This also has an angular effect. So when the Doppler angle is bigger, we can see the spread is bigger. When the Doppler angle is smaller, we see the spread is smaller. So this says that spectral broadening gets worse as the angle gets bigger. So whereas 60 degrees is not wonderful, it's certainly a lot better than 70, and 70 is a lot better than 80. Well, let's make it practical. So here we have two cases where nothing was changed other than the Doppler steering angle. So here we can see, let's start on this side. Here we can see this is the Doppler angle and this is 70 degrees. Notice the loss of the spectral window here, and the peak velocity is read to be about 80 centimeters per second. Now, by changing the steering, I was able to make the Doppler angle smaller. The Doppler angle is now 55 degrees. We now see the spectral window. We don't have that broadening. And we see the peak is around 60. This is artifactually spread, increased. So let's look at the error. 80 minus 60 is 20 over 60 is a 33% overread in the velocity, just going to 70 degrees. So we can see now there's two good reasons why we don't want to be at larger angles. The first is that any angular error about that, because of the nonlinear aspect of the cosine, causes huge errors in the velocity measurement, hence pressure gradient. And then because spectral broadening gets worse as the angle gets bigger. So, to conclude, the Doppler shift is obviously angle dependent. In fact, it depends on the cosine of the angle, which is why we spent the time learning the cosine. The user must specify the angle to use for angle correction, and it does so by setting the flow indicator. So if you set that flow indicator incorrectly, then angle correction is a misnomer because we're not really angle correcting, right? We're correcting for the wrong angle and therefore telling the wrong velocity. So incorrect alignment of flow results in incorrect angle correction. And even if you're really, really, truly careful, it's not possible to always be within, say, plus or minus 1 degree of the actual flow direction. So there will always be some degree of angular error. And this is why it matters that why we don't want to use larger Doppler angles. Because since the cosine changes faster and faster and faster as the angle gets bigger, an angular error around 7 degrees is a lot bigger than the error around 60 degrees, which is bigger than the error around 50 degrees. And also what we saw is not only do we have that problem, that larger Doppler angles result in greater spectral broadening, which also can result in incorrect peak velocity measurements. And therefore, if we're going to make pressure gradient measurements, errors in that as well. So that concludes the lecture. And I just want to point out the meaning of life. I figured it out a long time ago. This is my family, if you haven't guessed. Lots of kids. And so we're at the point of opening up for questions.
Okay, thank you very much, Frank. And at this time, we'll begin the Q&A session. From IAC, I'd like to introduce Marge Hutchison, Director of Accreditation for Vascular Testing. She will be assisting us with the Q&A session today. Marge, would you like to start us off?
I would. Thank you, Kelly. And thank you, Frank. Just an excellent presentation, as always.
Thanks, Marge.
You know, we have some cardiac people on as well. And the first question talks about why angle correction cannot be used with CW Doppler.
Okay, so first, I love the question, and I was anticipating this. It's not that it can't be used. It can be used. It's that we don't teach it in cardiac. And so now the question is why? And there's actually no real reason why we don't, but I have a belief as to why we don't. So let's just take a few moments to talk about this. So actually, if you go into CW Doppler, you have the little diamond there, which represents the area of the best overlap between your transmit and receive beams, okay? There actually is a flow indicator, but it's buried on the line. And so if you go onto your ultrasound systems, you look somewhere on there, there'll be something that says Doppler angle. If you rotate it, it'll pop off, and you can actually angle correct your CW. You can also, by the way, and we don't teach angle correction for PW in cardiac either, do we? So it doesn't matter if you're doing CW or PW in cardiac, we don't teach angle correction. So now the question is, why not? And are there times where angle correction truly would be appropriate? So first of all, remember what I just said, that if we believe that it flows at 0 degrees and we're off by, say, plus or minus 10 degrees, the cosine varies by only about 1%. So a 10-degree error around 0 or a 10-degree error around 180 degrees is only going to give you about a 1% error, not that big, so angle correction doesn't become as important. Whereas in vascular, where we have a carotid, and we're at angles like 60 degrees, a 10-degree error, as you saw, represented about 30% error in the velocity. So in the cardiac world, because we have so many different potential places to image from, right? We can go from the apical view, from the peristernal view, we can go subcostal, right? We can from the suprasternal notch, we can slip it into costal spacing. It's assumed that you can always find a way to get a line to flow, such that the flow is either straight at you, 0 degrees, or straight away from you, 180 degrees. And your job is to work until you do get as well a line to flow as you possibly can. With that said, are there times when you cannot truly get right down the pike? And the answer is yes. So many times we'll see cases of TR, tricuspid regurg, that are eccentric, and the best you can do is be off by, say, 20 or 30 degrees. In this case, the velocity you measure is off by about, so cosine of 30, 2867, about 14%. So the error in the pressure gradient is off by about maybe 25, 30%. And yet, so in this case, would it be appropriate to angle correct if you truly cannot get the angle? And the answer is yes, it would be. And yet we don't teach it. And I'll go back to that in a moment. The other case, if you have the ascending branch of the aorta and you're coming from the suprasternal notch, it's very unlikely that you're going to get directly aligned to that flow. You're going to be off by some angle. And just because of the geometry, right, where the notch is and where that ascending aorta is. And so quite frequently we're off by a fair number of degrees. And again, the velocity measurements are suspect at those points, and still we don't teach it. Here's why I think we don't teach it. I think there's a fear that, first of all, people would have to understand this to a much higher level than most people are taught. But second, there's a fear that if we teach angle correction, people will get sloppy. And instead of really truly searching out the entire volume by moving that transducer as much as they can, slip it into intercostal spacing, keep angling until they peak up the velocity, that people will just say, well, I'm going to angle correct anyway. I'll just take the measurement I have and angle correct. And that's a problem because you won't be just off. Remember that picture I showed you of the two different angles? So there's the angle you can see on the ultrasound screen, and then there's the other angle that you won't have corrected by. So if you don't really search out that volume, you can still be off by that other angle, and your measurements will get worse and worse. So if we could make sure that people really, truly search out the entire volume, and only then angle corrected in cardiac, we would actually see smaller error bands, and it would be better. But because generally people are able to get to 0, 180 degrees, those errors around there tend to be small, and therefore we don't teach it generally in cardiac.
Okay, thank you, Frank. So then the question arises from the vascular people is we are taught 45 to 60 degrees, but what if we could get a good angle at less than 45? Is that appropriate to go lower than 45?
Okay, so it's a very complicated question. I will tell you that I am in the process right now of releasing a paper with Anne-Marie Kopinski and Gene Zeeler and Carrie Olmstead and a few others, which actually talks exactly about this idea. And so the idea of 45 to 60, I'm going to say something that seems somewhat heretical, but I will tell you that the foundation of this paper basically says that 60 degrees at one time was a very good number, and that's what we wanted because of the limits of what the actual technology could handle. But as we saw, smaller angles are actually better. The problem is that you can't generally maintain angles that are much smaller because of the basic geometry, right? Unless the vessel is tortuous, you're not going to be able to get to angles consistently less than 45 degrees. So we want consistency because we want the measurements to be made at multiple locations to have the same angle. And so for that reason, we generally say try and keep it between 45 and 60. With that said, let's use some common sense. If you have a truly tortuous vessel, so the vessel is twisting and the vessel is doing something like this, okay, and you can get better angle down pike, well, it probably makes sense to make the measurement there and then report the angle. That's much better than doing something really strange where you move the transducer way up under the jawline, really crank up on the patient, and then angle it badly and get a bad angle and say, well, I forced it to get to 60 degrees or 40 within that 45 to 60. At that point, it doesn't make sense if you're having to go through twice as much tissue to achieve that angle. So common sense has to rule here. Basically, what we say is 45 to 60 is what we can do repeatedly. So that's the standard right now. That may change in the future, depending on where this research goes. If there's tortuosity and you're going to get a smaller angle, then you should specify, measured at 30 degrees. If by chance the geometry does not allow you, no matter what you do, by heel toeing the probe, by electronically steering, by doing everything you possibly can, and you can't achieve an angle less than 60 or 60, and it's bigger than that, let's say it comes out to be 7 degrees, well, of course, you're still going to take the measurement. But then what you should do at that point is notate and say, note, bad angle, 7 degrees, best it could achieve, risk of spectral broadening. And that warns the person who's interpreting that the velocity is suspect to be higher than what it probably really is because of the risk of spectral broadening.
All right. Thank you. I hope that helps people. We see a lot of these issues that come up in the cases that people submit, angle correction. What about being parallel to flow or parallel to the walls?
Okay, so we're going to open every can of worm we possibly can today. So there's raging debate in the field about this. And the research that's been done, I will tell you, I do not believe the conclusion that people drew with statistics, because statistically, I believe that research was done incorrectly. So what people have said in the research is that you should align to the flow, to the vessel walls, and not the flow, okay? And I don't believe that. I believe you should align to flow. So let me give you an example. So let's say I have a plaque that looks like this, which causes an eccentric jet. And let's say I can see these vessel walls, but the velocity, the flow, is actually moving this direction. If I align to the walls, I'll be off by this angle, and my velocity will be incorrect. Now, the reason why people say align to the vessel walls is they did a study, or a series of studies were done, and they said statistically they saw no difference between the measurements that were made if aligned to the vessel walls or to the flow. And therefore, since it's easier to align to the vessel walls, that should be the criteria. The problem with that study, and this is a little bit hard to understand, but I'll try and make it clear. The number of eccentric jets they had in that study was almost nothing. And I think there were 1 or 2 in all the cases. Almost all of them were cases where the flow really was straight down the pike. It wasn't eccentric, which means statistically, if you have 1 or 2 cases where it really would have mattered, and you have 500 cases where it doesn't matter, it basically gets washed out in the average. So the only way that study really has to be done is you have to look at only eccentric jets, and then look at the difference between the measurements made aligned with the wall and the actual aligned with the flow, and then considering how different those are, and I think it'll tell you a different story. So I have an easy way I get around it without, so I don't get into trouble with everyone around me by yelling at me. I basically say, align to the walls of the flow. And by saying that, this is the walls of the flow. So I want to align to the walls of the flow, and that's my answer, align to the walls of the flow. But you will find many people in the field who will say that you should align with the walls and not the flow.
All right. Well, thank you, Frank. We're just about done with our time now, and there are many questions left. And I just want to tell everyone that your questions will be answered by email in a few weeks. We'll take care of all of your questions. So if we haven't read it out loud, don't fear. And I think Kelly's going to come back on and kind of close us out here.
Okay, thank you, Marge. And thanks again, everyone. And a very special thank you to Frank Miele for his presentation today. Please feel free to contact IAC with any questions that were not answered during the Q&A session. To receive continuing education credit for attending this webinar, please complete the survey. The survey will appear on your screen automatically at the conclusion of this live session, and also be available from the IAC webinar portal for 3 business days. On the left side of the My Account page, you'll click on Webinars, look for the title of this session, Physics for the Clinical Cardiovascular Sonographer, Beneath this title, you will click Review Event. On the left, select the Evaluation tab, then click Take Evaluation to complete the survey. Your certificate can then be accessed and printed from the very next screen and anytime thereafter through the CE transcript section on the My Account page. If you have any questions about the survey, please contact us at webinars@intersocietal.org. Once again, we thank you for joining us today and appreciate your participation.